Welcome everybody to the GRASP SFI seminar. We are starting in time since it's also hybrid, and I'm very glad to host today Professor Sridhar from Brown University. He received his PhD at the Max Planck Institute, and then he did his postdoc at Stanford. He is one of the initiators of the neural fields movement, and he holds also the repository for everything about neural fields at Brown University, which I don't know if I'm going to show a brief link, but I heavily recommend it. He also organized a really beautiful workshop at CVR. He received the NSF Career Award. This is really the most prestigious thing you can get while you're on tenure track. And today we're going to talk about learning to generate and arrange the object shapes.
Thank you, Kostas. Thanks a lot for the kind introduction. It's really great to be here at the GRASP Lab, my first time here, and to hear from all of you. I think it's doing some really exciting work. And also, initially, I was going to give this talk remotely. Costa suggested that I should come here in person, and I jumped at the opportunity, and I think it's been well worth the effort. So I'm really glad to have met you all in person. Yeah. So today I'm going to be talking about learning to generate, edit, and arrange 3D object shapes. But before I do that, I want to take an opportunity to thank all of my students. I mean, my students led pretty much all the work that I'm going to be talking about in today's talk, especially Rao and Rahul Vistani. So I'm going to be talking about two projects in particular. Those were led by my PhD student, Rao and Rahul. All right, so let's get started. Now, as humans, we lead extraordinarily interactive lives. You might go to a supermarket or a market. We use our hands to pick up objects such as vegetables. We inspect them before we purchase them. We build large infrastructure. We use, again, objects like trains and machinery like cranes to pick up objects like pillars, wood, and so on and so forth to build buildings and bridges and so on and so forth. We use our hands in very highly dexterous ways to manipulate small objects in very fine ways, right? We might use our hands to cut ginger or cut tofu, things like that. So these are really, this requires very fine motor skills, and we're able to do that. And we're able to manipulate small objects and big objects at the same time using our hands. Now, one of the grand goals of robotics and computer vision kind of tags along with that is, if you want to build robots that can help solve any tasks, help, for instance, in assistive robotics, or help automate construction, perhaps cooking and woodworking and so on, we need to build robots that can actually perceive objects and see. Robots need to have an understanding of objects that they see in the world, and we need to have a 3D understanding of these objects. If we can do that, then we can build robots that have similar capabilities to humans in terms of manipulating objects at different scales and using fine motor skills to manipulate them. So that's one of the things that we need in order to realize this vision of robots that can operate in household environments and so on and so forth. Of course, robots have kind of checkered history with objects. I'm sure many of you have seen this video before, right? From Boston Dynamics, a robot trying to place an object on a table. It fails at that, pushes the table down, and then falls. I'm being a little bit dishonest showing this video because it's kind of cherry-picked from several years ago. I mean, Boston Dynamics has many successful robots after that, right? Like Stretch, for instance, can solve a similar task, both using perception as well as using a mobile manipulation robot Stretch that you see on the right. And of course, lots of other companies and research labs have worked on this problem as well. To solve problems like this, where robots closely interact with objects in everyday environment, we need to solve challenges in perception, control, planning, as well as in control. My talk today will approach this from the perception perspective, like what kind of computer vision problems we need to solve, what kind of computer vision challenges exist, and how can we address them one at a time in order to eventually achieve this goal of building robots that can seamlessly manipulate objects. So my group at Brown primarily works on 3D computer vision and machine learning for different kinds of applications. We're interested in building 3D computer vision and machine learning tools for understanding human motion. So this includes things like human body motion, what is the space of poses that that human bodies take when moving in the environment. We work on visual understanding of human hands, like what is the pose involved in human hand motion. We're also interested in objects, so we built 3D computer vision machine learning tools for understanding the pose of objects, the shape of objects, and trying to reconstruct these objects from images and so on and so forth. We're also interested in bringing these two things together. How do people interact with things? How do humans interact with objects? So we're really interested in building computer vision perception methods that understand how people interact with objects in daily environments. And of course, to achieve all of these tasks, we also work on fundamental techniques. And these techniques include the theory of 3D computer vision, neural fields that are more and more being used in the computer vision community for solving these kinds of tasks. And these techniques plug into any one of these different areas that you see. All right. So let's think a little bit more about what it means for us to gain, or robots to gain, visual 3D understanding of objects. For a robot to look at an object and try to understand something about the object, we can think of it as the robot has to know something about the properties of the object. And these properties, we can roughly classify them into intrinsic properties. So that could be something like object class, it could be something like the shape of the object, or the articulation. These are called intrinsic properties because to figure out what the intrinsic properties are, we don't need an external reference of sorts. Right? It's just unique to the object itself. We also need to know something about the extrinsic properties of the object with respect to some other global reference. Right? So this could be things like the position, orientation, velocity, and so on and so forth. So these are a non-exhaustive list of object properties that we might typically be interested in order to better understand objects. Of course, knowing the properties of these objects, the intrinsic and the extrinsic properties of objects, allows us to solve various kinds of tasks, which might be useful in robotics and other areas as well. For instance, we might want to know what objects the robot is looking at. We might want to know the 6-dot pose, the 6-degree of freedom pose of the object, the position, the orientation. We might want to know the shape of the object. We might want to know what happens if we edit the object. Perhaps we might want to know how we can arrange these objects, how to orient them in consistent ways, like all chairs should face upright. So there are different kinds of tasks that are enabled by knowing these properties of objects. In this talk, I'm going to be focusing primarily on 3 such tasks: shape generation, shape editing, and arranging objects in a canonical way. So these are the 3 things that I'm going to be focusing on in this talk. All right, so I'm going to be talking primarily about 2 projects, recent projects that some of my students have worked on. The first is ShapeCrafter, which is a method for learning to generate and edit 3D object shape distributions. Second, I'll talk about ConDor, which is a neural network that learns to canonically orient objects belonging to a certain category, in this case, chairs. And finally, I'll present some more recent work that we've been working on that extend these methods to other kinds of objects, like articulating objects, dynamic scenes, and also using emerging representations like neural fields. All right, so first, I'm going to be spending a little bit of time on ShapeCrafter. So ShapeCrafter is a fixed condition 3D shape generation model, but it's also a recursive model, meaning we want to generate shapes, but we also want to edit these shapes through language prompts. Right? So we might say, give me a chair, and then once I have the chair, I want to make sure the chair has separate legs and so on. So I'll show you several examples. And this was a project that was led by my PhD student and other collaborators. Okay, so let's consider the following scenario. We have a 3D designer who wants to fulfill a requirement from party A. So party A might say something like, please design me a building which has 5 floors, base, and a high tower. Right? So the designer goes away to his favorite CAD application, his or her favorite CAD application, and builds this kind of a CAD. Sends it back to party A, and party A says, okay, this is great, but I want the tower to be narrower and taller, and now I want it to have 14 floors. You might say that. And the designer, a little bit flustered, but they go back and continue to change the model. And this process continues for a while, until eventually both party A as well as the designer converge onto something that they're both happy with after perhaps a lot of frustration. So this is like a typical process that someone who's not proficient in CAD model, how they might work with a CAD model designer, 3D design. Now, one of our goals in this project was to see if we can replace this 3D designer and the frustration that comes with people interacting with each other with an AI system. Essentially, a generative model that can enable this kind of recursive editing of a shape. So you start off with some basic shape, and then you kind of edit this shape as you go. These slides were designed by my PhD student, and funny enough, she actually striked out the please design me part here, so we don't have to say please to our robots anymore. Okay, so our goal is to generate and edit 3D shape recursively using language prompts, such as this scenario that I just showed. This is, of course, useful in 3D design, perhaps in design of models for augmented reality, virtual reality, but primarily our focus is to see if this can actually be useful in human-robot dialogue, for instance, in object search activities. That you might say, I'm looking for a specific object, start off with a high-level description of the object, and as the robot searches for this object, we provide more and more fine description of that. Of course, there's been plenty of work in generating 3D shapes from text. This is a non-exhaustive list of some of the more recent work. Right? We've all seen work such as Dream Fusion, for instance, which produces very high-quality models. However, most of these models have some limitations. First of all, these methods do not support recursive generation. These models tend to be a single forward pass model, right? So you provide a text prompt and you get a 3D shape. There is really no way for you to edit these 3D shapes within these models. Second is these models tend to produce a single instance for every text prompt. So if you say I want a chair, they produce a single chair. But chairs can be of many types, and these models don't necessarily, even if they do capture it, they're not necessarily able to express this in terms of the outputs that they produce. And finally, models that use neural fields, for instance, can be very computationally expensive. So it might take weeks for us to train some of these models and to get good results.
But in image generation, we can put conditioning both on text and existing. Right? And I could take, this for 2D, I could do it easily without having been trained in that way, but still I can, let's say, implement it.
Right, yeah.
And modify things.
Yeah, you can certainly do that. And I'll show later that in some of the experiments, we actually did try that with existing models that can produce 3D shapes. But what happens is that the recursive process doesn't produce coherent results. So you end up changing the shape significantly. Yeah, I might have a slide that shows. All right. So let's look at the problem that we're trying to solve. So our input is a natural language description of whatever object that we want to synthesize. So we start with something that says a chair, right? And then we want a model that can produce different kinds of chairs. So here we're showing 4 instances of chairs that is produced by such a model. We then want to add some additional qualifiers to the original input that we provided. So in this case, we're saying we want a chair with no arm or separate legs. The back is slanted with a flat back and so on. Okay. So given this additional qualifier, we wanted to produce shapes that satisfy this additional input that we just provided. Right? So here you can see when we have this model here, we say we don't want any armrests, and we now synthesize new shapes. Again, not just a single shape, but a distribution of shapes that does not have the armrests. And we can keep repeating this process. Right? So we can add more and more qualifiers until we are happy with the final shape. Yeah.
Did you just have that original paragraph?
generative model, shouldn't it be able to produce a wide distribution of chairs, like, and then maybe the designer can just select what chair they want, like instead of going.
Sure. Many of these models actually are, they do implicitly have some kind of a distribution of chairs, right? So they can be sampled to produce this. You want them to be consistent, right? So you want them to say, in this case, it's the first instance here that is being modified. So it's not a different chair that is being generated here. So we somehow maintain the history of how, what is the path that we took from going to this shape here to this shape here. And I think that's the difference between just having a generative model versus a recursive generative model. And this process is also close to how humans would actually do it, like when you're interacting with 3D designer, we do this in a recursive fashion. Okay, and we might sometimes also want to synthesize shapes that are out of distribution in some sense. So for example, this example here, we want the legs to look like armrests. And you can see that these are examples from our method. So you can see that the legs actually resemble kind of an armrest, a wide armrest. You can see some of these out of distribution stuff happening as well. All right. Okay, so building such a recursive text condition generative model has a few challenges. So the first challenge is that there is no data set that we can use for producing such a recursive, or for building such a recursive model. The second challenge is that we want to produce high quality shapes, especially because some of these recursive prompts that humans use to modify objects tend to be about small scale detail that we see on objects. So things like armrests, legs, slats, and so on and so forth. Right? So we want a shape representation that can actually faithfully model these small scale. And then finally, we want to build a model that retains this notion of history, that it has some kind of memory of where we started and how we want to modify this shape. So these are the three challenges. So in this work, ShapeCrafter, we address these three challenges, and I'm going to be talking about these challenges and our solutions. So first, let's start with the lack of existing data sets. So most existing data sets, both for text-image pairs as well as for text-shape pairs, are limited to single shape, text prompt shape pairs, right? So most of these data sets have a one-to-one mapping between text prompts and shapes. But in the case of recursive shape generation, we want to have many-to-many mappings. So we might want to start off with a particular text prompt. Even if we change the order of the text prompt, we wanted to produce shapes that look similar. Right? It doesn't matter if I modify the legs first and then the armrest, or the armrest first and then the legs first. Right? So there is a many-to-many mapping kind of a data set that we need to solve this challenge. So there are some existing data sets. For example, the most common data set is the text-to-shape data set, and then the shape plot data set. But none of these data sets satisfy what we need. These are both one-to-one mappings. So one text prompt has exactly one shape. Right? So that's so what we did to address this problem is we augmented an existing data set. So we actually took the text-to-shape data set, which is a one-to-one mapping between text prompts and shapes. I probably don't have time to go into the details, but I'm happy to discuss this later. Is we use some NLP tools, particularly we used constituency parsing, where we take this really long sentence that describes this particular shape in the text-to-shape data set. We parse this sentence into its constituent parts using constituency parsing, and we get essentially a hierarchy of these different phrases. So, for instance, you might say if the sentence starts with just a wooden, that can be associated with a bunch of chairs that have this kind of wooden texture. Right? We don't look at appearance, but it turns out that appearance characteristics also bleed into geometry. So in this case, we're only looking at geometry. I might say something like a wooden dining chair, and we mostly get shapes that don't have armrests that resemble some kind of a dining chair. We might say a wooden dining chair with 4 legs, and when we do that, any chairs here that don't have 4 legs, that have wheels and stuff, would not be included in the data set. And then finally, as we have more and more qualifiers that add more and more information, you'll see that we have mappings here that correspond to only chairs that have slats, which is what is requested in this particular prompt. So we did this automatically. So we use constituency parsing. There are tools in the NLP community that can parse sentences. And then we do a little bit of post-processing to kind of make sure. So we took these really long sentences, broke them down into constituent parts, and then we did this for all possible phrases that we have, and then matched up sentences that look similar. So multiple sentences in the text to shape data set could start with a wooden, and we match them all up.
And then if you add in like the start back, get the start back in the text frame.
Correct. Yes. Yeah. So this all of this comes from the text to shape data set.
When you try to find an existing, you don't add an existing shape. You don't add any values.
No, we don't add any. This is all just existing, augmenting the existing data set. I think we probably augmented about 6 times larger than the text to shape data set.
You augment the data set with text.
So it's the same text description, but different lengths essentially. Yeah. Right. So we have actually text to shape has these really long sentences, so we can actually break it down into smaller parts. So we would essentially have small and then larger, and so on. As the prompt becomes larger, we would have fewer and fewer shapes that satisfy them. And also sometimes the same phrase could be expressed in different ways. The dining chair could be a chair for dining. Right? So we also look for that. So we look for semantic similarity as well. So we match up those phrases that semantically are similar to each other. And there are pretty good tools in the NLP community like Roberta, which can help us figure some of these things. Okay, so that's the first challenge. Again, I'm happy to go into more details. I have some supplementary slides for that at the end of the talk. So the second challenge is how do we model high quality shapes? Because oftentimes when we describe attributes or when we add information about objects, we're interested in small details, things like armrests and legs and so on and so forth. So we need a 3D representation that can faithfully capture some of these small scale details. So we were looking at the literature for some of these 3D representations, and the thing that worked the best for us was these vector quantized implicit shape representations, which use VQVAEs to represent shapes. And the key idea here, which is described in the Auto SDF paper, if you're interested, is to divide a shape into a bunch of patches, and each patch is separately encoded, independently encoded into some kind of a feature, and these features are quantized. And the quantization happens during using a learned code book, which was also learned together jointly during training. And then these each patch here is assigned to one particular code in our code book. And then there's a decoder that decodes each of these features independently, and what we get is a faithful representation of the shape. And this seems to produce the best performance in some of our experiments compared to other methods like convolutional occupancy networks and occupancy networks and so on. We also do a little bit of addition to this. What we do is we want this representation to model shape distributions, not just individual shapes, because we're trying to capture category level variation in shape. So instead of just trying to predict the exact index in the code book, we also predict a distribution of it, the probability distribution of how confident this particular feature is that it belongs to code book 2 or code in the code book 2 or 37 or similar to that. So what we have is essentially a probability distribution features. Okay, so what this allows us to do, and again, I'm happy to go into the details here later, is it allows us, it gives us a way to model these high quality shapes while faithfully capturing some of the local details which people might express when they're talking about or describing objects. Okay, so the final challenge is how can we now build on top of the data set that we have and the representation that we have a generative 3D model that is capable of recursively generating these 3D shapes. So starting off with an initial shape, retaining the memory of what that initial shape was, and editing that shape distribution as more and more text phrases are added. So, I mean, the simplest version that we could have tried is a simple generative model. We could take our vector quantized implicit representation, and given some kind of text input, we have our data set. We could build a generative model that directly maps to an output. So this is what we talked about a few minutes ago. So we could build a generative model that looks like this, and this works. However, this is not suitable for recursive generation because there is no notion of history. Like there's no memory of what the artificial shape was, and gradual editing of that particular shape. So that's something that's lacking in this particular model. We can also have a conditional generative model where we say that we want to take a prior distribution of that shape in the form of this vector quantized feature grid that I talked about earlier. So we could say, I want to condition this prior probability distribution with some text, and then have a conditional generative model that is able to synthesize shapes based on these two inputs rather than just the text. So that's another thing that we could do. Again, here, this is actually the backbone of recursive generation, but this is just a one-step process. Right? So there is no recursion here. So what we essentially do is we have a recursive process in this condition generative model. So we start off with a probability distribution from the prior step, which is essentially this feature grid from the prior step. We have a text that is conditioning and being fed into this recursive generative model that conditions it both using the prior probability distribution as well as the added text prompter, and we're able to synthesize shapes in a recursive fashion.
So for the how did you feed that?
I'm going to talk about that in just a second. Okay, so to answer your question, what is this recursive generative model? That's the next question. Right? So our recursive generative model has three components. The first component is the text feature extraction model. And for this, we use BERT, and we use a linear projection layer, which is just an MLP without all the nonlinearity. We just have a bunch of linear layers. And we project those directly into a feature grid that's the same size as our shape feature. So we essentially take the BERT features and project it onto this feature grid over here. The second part of our model is the text and shape feature concatenation. So we need a way to combine the text and the shape features. And for this, we just use a bunch of residual blocks, which take both of these input and produces some features, which are then concatenated with the features from BERT, essentially, the text features from BERT. Sorry, not concatenated with that. They produce a separate feature grid after taking this input. The third one is the third component is the generative model groups. So the third one is the shape feature refinement model. And for this, we use a random transformer from this particular paper, pixel transformer. Random transformer is a non-sequential autoregressive model. So a typical transformer retains some notion of sequence, whereas in this random transformer, we have this paper modifies this into a non-sequential autoregressive. And in our experiment, using the random transformer was better than just using a transformer for that particular one. And empirically, we discovered that therefore we use that for the shape. So these are the three components of our recursive shape generation. I'm sorry, say that again. Inference time. I have a real-time demo, so that might tell you something about that. All right, let's look at some results. So I'm showing a bunch of results here, but I'll walk you through. Sorry, that is sampling. So this feature grid, these are probability distributions. So in order to get a shape out of this, we need to sample those probabilities. Exactly. Then we have a random sample. So the way we would edit the shape is that we would fix the random seed. So we would initially start with one random seed and then keep providing the same random seed. Okay, there's a bunch of examples here, but I'm going to walk you through the salient features of these results. So first of all, so we have only two categories, chair and table. And the reason for this is because text to shape also has two categories. So we don't have data for other categories. So we're limited to what text to shape originally gives us. One thing that we notice is that we are able to handle fairly long sequences. Right? So in this case, we start off with a chair. By the way, there are spelling errors in the text prompt as well. Right? There's black and chair, everything is misspelled, and our model is able to handle it just fine. Right? And this is not a feature of our model; it's a feature of BERT. Right? So you can do things like that, and you can do this for several sequences. So in this case, we are doing like 5 editing operations on the shape distribution using the same random seed. So you can see how the shape evolves from something that looks like an office chair do something that looks like a circular seating arrangement. We can also do global modification of the overall shape. Take the case of the bench, for instance, or a table, for instance. Right? So we start out with a table that doesn't have any seating arrangement, but then we are able to edit to add these additional seating components to that model. We can also do part level modifications. So as I mentioned earlier, we can have a curved seat. We can add armrests or remove armrests. We can do things like that that edit certain parts of these shapes. We can also change the shape. We can do out of distribution, right? So for instance, in this case, we are estimating like an L-shaped table, which is something that we originally did not have in the we can also do local detail modification. For instance, in this particular case of the tables, adding 4 short legs actually results in adding 4 short legs to this block table. And then finally, again, this is an example of out of distribution generation. Right? So L-shaped table, half circle shaped table. These are examples that were not in the original data set. Right? And we are able to extrapolate out of distribution text blocks as well.
Srinath,
yeah.
Have you tried like the mechanical way? You press that add with arm, and then you have without arm.
Yeah, good question.
What happened?
Yeah, good question. I don't think Rao has tried that. It'd be useful to see what happens if we do something like that. Yeah. So try to annoy the yes. All right. Of course, this is not perfect. ShapeCrafter isn't perfect. There's plenty of limitations and room for future improvement. First of all, although we use the the vector quantized representation, we still miss some fine scale details. In this case, you can see that the back has it's not symmetrical. There's all these little things that shouldn't be there, noise and so on and so forth. Right? This is something that I don't believe is a limitation necessarily with the way we structure our generative model, but more so with the representations that we are using. So I think there's a lot to do in terms of the representation itself. And then finally, the method we use often results, because we use the random transformer rather than the traditional transformer. We see that often results in losing notion of this memory. Right? So editing the same shape, sometimes it loses track of what the previous time step was, and we observe this in some of these cases. So that's also another limitation with this method. Okay, so since I'm running a little bit behind schedule, but since we talked about the video, I'm just going to show a small snippet of the real-time demo. This is still work in progress, and this is
a chair with a square back. It is made of metal.
You can see the results pop up over here.
It is an office chair. It has wheels and armrests. It has a very long back.
But in this step, you'll see that it kind of preserves the shape and but anyway, just to show.
The chair is comfortable.
Yeah, the last bit. All right, I should probably continue now. But anyway, so some of the video here is sped up. So especially during the inference, there's actually a lot going to compute clusters, sending the results back, and then loading it up. So it's probably a little bit shorter than what you see here. But I would imagine it's in the order of less than a second. Okay. Yeah. Just 2 classes, tables and chairs, because that's the data set that text to shape has. So we don't add any more data text to shape. And that's also another limitation, I should say. It's just limited to these 2 classes. I think the reason for that is because we built on top of text to shape. So I think if we had access to more, if there was more data sets like text to shape, then we could probably extend. All right, so the second project that I'm going to talk about, and I should probably be a little bit brief on some of the details here, is ConDor, which is a method for canonicalizing the 3D pose and of partial shapes as well as full shapes. And I think this is very relevant to some of the work that many of you are doing in terms of equivariance. A quick quiz here. There's a bunch of chairs on the top. I'm going to flash 4 other chairs here. I want you all to tell me which one looks the same orientation as these 3 chairs. Ready? See, unanimously see, right? So that's the right answer. So the task that you just solved is called the mental rotation task, and it's been extensively studied in cognitive science, right? Humans are very good at it. That's why we're able to operate in an environment, figure out if things are upright or if they're not upright, make them upright, and so on. Right? So this is again a capability that we want our machines to have as well, because if you want a robot to set all these chairs upright, we need the robot to understand what is up and what is down with respect to the chair. Right? So that's something that we need to figure out. So the goal of this particular project was to help us figure this out. How can we build AI systems? Or can we build a neural network that can understand canonical orientation of classes of objects? So for chairs, what is the canonical orientation of chairs? And of course, this is a hard problem. Needless to say, I don't have to pitch into the choir here. It's so hard that it's actually used as a captcha. If you go to some websites like LinkedIn, right? Canonically orienting this little pad here is so hard that machines cannot get solved. Right? And I think that kind of indicates the level of difficulty of this task. Okay, so there's a bit of a dark secret in the 3D vision community as far as canonicalization. And you can see that clearly in both of these images here. This is the ShapeNet dataset, and that's the ModelNet 40 dataset. And if you notice, every model in the ShapeNet dataset has instances that point in the same direction, which means that somebody actually manually oriented all of these instances so that they all face in the same direction. So ShapeNet Core in particular has this kind of canonical orientation. Most of the work in generative models in 3D vision, in 3D shape generative models, make use of the ShapeNet Core dataset, which actually significantly makes the problem significantly easier, right? Because you don't have to account for the rigid pose variation that you see. So that's kind of a dark secret that nobody talks about that much. I mean, this is the same as saying, imagine if you had an ImageNet, but this only works for one particular orientation, right? So if you had a data set of cars, but you train a model only for front-facing parts of the car, or only for the side-facing of the rear-facing parts of the car. Right? But if you had something like this, then if you had a Tesla which goes and hits the car in front of you because it wasn't trained on models of the reverse side of the car. Right? So it's the same as this is what we're doing in computer vision. Right? We're not taking into account these kinds of orientation changes. No, I found this somewhere. Not valid. Okay, and the 3D models that we find on the internet or we capture from depth images do not have canonicalized models. Every person likes their own canonical frame when they create a 3D model. So there is no match. We cannot use internet models to build such problem.
What is the right image from? Where is it?
Good question. I probably have it somewhere in my comments. I can find that for you. It looks like similar. All right. Of course, we can solve this problem in a supervised way, right? So we can say that for any object that we might encounter, let's densely label the object in some kind of a canonical frame. So this is some work that we did a couple of years ago for normalized object coordinate system. And what we have in Knox is for categories of objects, we specify what the canonical orientation should be. Right? And we can build a neural network that tries to give an observations of an object, tries to map it to this canonical frame. Right? So this is doable and this works. However, this is fully supervised, right? And this is not, this requires very heavy labeling of each category, each instance in every category. It's similar to what we had in the ShapeNet Core dataset. That makes it very difficult for us to extend this to real-world settings where robots have to deal with tests that we observe from images or from depth sensing. So yeah, as Jan LeCun likes to put it, the revolution, we don't want the revolution to be supervised. Right? we don't want to use these dense. So what we wanted to do was take as input point clouds of common shape categories like chairs, tables, and so on. Either full shapes like what you see on the left, or partial shapes like what we might observe in depth images. We only see the front facing parts. And using this, we want to produce a canonically oriented version of the input point cloud, such that this is consistent over all instances in a given category. So that's our goal, to go from here. For the moment, ignore the colors. I'll talk about the colors.
What do you find complete? What is complete?
We don't care about consistent means, from I guess a semantic perspective, you expect the seat of the chair to be facing a certain direction, and we want that to be the same for all chairs. We don't care if it's pointing in this direction or in this direction. We only care that between instances they point in the same direction. Of the same class. So these are
Just aligning the pairs.
no, between all instances in the class. And sometimes these instances might look drastically different. And of course, we don't want to use any supervision for going from this class. So we want a solution that works across different kinds of instances in a shape category, and that does not use any additional supervision, human supervision. So a couple of definitions here. So the first is this notion of instance level canonicalization. So what do I mean by that? So here we have two different, we have the same aircraft instance, but in different orientations. Right? The first two are full shapes. The last one is a partial shape, sliced in half, essentially. Right? What we want to do is we want to discover this coordinate system that you see here that is consistent across these three shapes. So in this case, the green arrow is pointing upward from the fuselage, and that's the case over here, and that's the case over here. So we want something that is consistent. The notion of category level post-canonicalization extends this to instances within that category. So in this case, we have an aircraft here. We have a very different aircraft. In this case, the fighter jet. Right? And what we want is for the predicted canonical post to be consistent across these different shapes, and also for public. So this is what we are looking at. Okay. So it turns out that in order to do this, we need three ingredients, and I'm going to talk about these three ingredients. I'll probably be a little bit light on details since I'm running out of time, but I'm happy to talk about it afterwards as well. So the first ingredient that we need is this notion of permutation equivariance. Many of you are probably familiar with it. So we have a bunch of points over here. If we shuffle, and we have a neural network that extracts some kind of features or some kind of processing of this point cloud. If we shuffle the input ordering of the points in the point cloud, we want the output features to be shuffled at the same time. So this is the notion of permutation equivariance. The second ingredient that we need is rotation equivariance. So here the idea is if you have a point cloud that a neural network uses to extract some kind of features, if we rotate that point cloud using rotation matrix R, you want the features extracted by the neural network to also be rotated by some function of that rotation. So that's the notion of rotation equivariance. A special case of equivariance is invariance. And here the idea is that if you have two rotated versions of the same shape, you want to produce exactly the same feature. Okay. So that's this notion of rotation invariance, which is a special case of equivariance. And then finally, the third ingredient that we need is translation equivariance. So if you have a shape that is in a certain location, we translate that to a different location, we extract features, we want those features to be translation equivariant. The best example of this are 2D convolutional neural networks, which are translation equivariant. All right. So again, I'm going to be a little bit light on details here, but essentially what we do in order to achieve these three ingredients or to satisfy these three ingredients is we use these so-called tensor field networks. Tensor field networks are equivariant to point permutation, tree rotation, as well as to translation. So they satisfy all of the things that we need. We essentially extract some features which are equivariant to rigid pose, and those are the features that we use in ConDor. and these features satisfy the equivariance. All right, so of course, there's a bunch of work, including from Costa and others, on building 3D point cloud processing architectures that have these equivariance properties. We tried many of them and empirically found that TFNs work better. Especially, we tried vector neurons and steerable CNNs and spectral CNNs and so on. But empirically, TFNs seem to work better. All right, so I'll just give like the high-level overview here. So we take our input point cloud. We use a TFN, a tensor field network, to extract some features. And from those features, we have an MLP. These features are equivariant features, essentially. And all we have to do is select from those equivariant features one particular equivariance direction that gives us a canonical pose. So if we have features that rotate along with the input shape, all we need to do is fix one direction to be the canonical pose, and that satisfies the canonicalization that we're looking for. However, this only works for this particular shape. So if we have another shape that looks very different, we might get a different canonical pose here. So in order to solve this problem, we take the point cloud, compute the spherical harmonic function on top of the point cloud, get the spherical harmonic, and there is some theory, again, I don't have the time to go into this here, but there is some theory that says that you can interpret the features that you get from tensor field networks as coefficients of the spherical harmonics basis. And what that gives you, the dot product between the spherical harmonics and the TFN features, gives you something that is invariant, the invariance property that we're looking for. And that gives you a canonical point cloud that you see here. So this is like a very high-level picture of what we try to do. And we have a loss function that tries to minimize the loss between invariant point cloud and the rigid canonical pose that we estimate for instances in our question. Yeah. It's a good question. I'm not 100% sure about the details. I can double check that. I think we are doing this for different radii, but I might be. I can double check that. Okay, so these colors that I showed earlier. Well, it turns out that our method is also capable of performing some kind of unsupervised segmentation of the shape, just by adding an additional branch to our architecture here that takes the invariant features. And this actually produces segmentations that look consistent across different instances. So you'll see that the right wing here is blue in all of these instances, the left wing is brown, and so on and so forth. So when trained on a large shape collection, we notice that it actually produces kind of consistent co-segmentation. Okay, I'll just quickly flash through some of the results. The gray here is the input point cloud. These are other methods, compass, PCA, canonical capsules, and so on. And visually, we can see that our method performs better than some of these approaches. Each approach uses a different kind of equivariant architecture. Some use spherical CNNs, others use vector neurons, and so on and so forth. But we notice empirically that TFNs work better. I'm not going to go to the quantitative numbers here. We also do well compared to other methods. But I do want to point out that PCA, which is 120 years old, performs surprisingly better than many of these methods, including our own in some cases. Right? However, our method does beat PCA when it comes to partial shapes. So that was just something really surprising. Yeah, symmetry is one of the limitations right now. Right now, we don't handle symmetry at all. And I'll show some failure cases. Yeah, PCA also doesn't handle symmetry. I'm just going to quickly show some partial canonicalization results. So each column that you see here is one category. And this is the only input that we provide in it, which is the partial shape of that particular instance. And you can see that our method is able to correctly canonicalize even with just a partial version of that. The gray points here are not used during inference or during training, it's just visualization. All right, so failure cases, symmetry is the first case where we fail, especially when we have tables that have like the axis of symmetry or planes of symmetry. Right? Those are cases where we definitely don't do very well. Noise, clutter, very thin structures, and so on and so forth. So we can struggle with those. Code is available for this particular paper, PyTorch, TensorFlow, go to our website, access all of that. All right, so maybe in the last couple of minutes, what I'm going to do is talk a little bit about where do we go from here. I mean, this is still a very far cry from how I motivated this talk in terms of building robots that can understand objects better, but we still have a long way to go. And I can talk a little bit about some of the work that we're doing in my lab on trying to address some of these emerging challenges. In particular, what I've talked about so far focuses on generation, editing, and arrangement of static object properties. So primarily shape and the pose of objects. So that's what I've focused on so far. However, many of the things that robots do, that humans do, are interactive dynamic tasks, right? So we want to know about objects, articulating objects. We want to know about humans that move in an articulating fashion, and so on and so forth. I think those are all big challenges. Most of the work that I talked about is limited to single shape instances, right? So if you asked ConDor to canonicalize 2 chairs, you couldn't do that, right? And then finally, we used shape representations like implicit representations and point clouds. But there are emerging representations, neural radiance fields, and so on. So can we use some of these representations to solve this? So the obvious extension for ConDor is articulating objects. So we've been working a little bit on that. Here you can see an example of an extension of ConDor, which works on articulating shapes. And here the goal is to discover parts, identify joints, joint limits in a self-supervised fashion. So we take ConDor, extend this to parts, and then we're able to get some initial results that look like this. So that's one thing that some of my students are working on. Of course, there's some really nice work in this direction by Jeffrey and Costas, CADEX, which also goes along similar direction. Another thing that we're interested in is collections of shapes, not just single shapes, but if you have a bunch of shapes, what is a canonical arrangement of a collection of shapes? Right? This is also something that we're interested in and working towards. And finally, another, I guess, a dark secret with 3D computer vision is we tend to operate on synthetic data sets like ShapeNet and ModelNet. But for real world tasks, we need real data. And this is something that is currently lacking. We don't have very rich, large real world data. So in my lab, we are building a multi-camera capture system, which is, I would say, kind of designed for the NERF era in some sense. So this camera system looks like a box, about 1 meter cube. It has 54 cameras within this small space from all sides, not just from the top, but bottom, side, top, and so on and so forth. Here's a bunch of my students assembling all the cameras in this multi-camera system, and you can see a little bit of the data that comes out of this multi-camera system. So we have about 54 software synchronized videos that we can collect at about 120 frames per second for each camera. And the idea is that the questions that we want to ask using capture systems like this is, can we build data sets that can enable us to capture articulating shapes like human hands, interactions between human hands and objects, perhaps even small robots and objects. We'd like to understand how these kinds of interactions take place. Here's just a couple of examples of some NERF-like reconstructions that my students produced using a simulator. This is not real data. This is simulation. And talking about neural fields, Costas mentioned this earlier. I just want to point you to this resource that we have, neural fields in computer vision. This is an effort that we started a few months ago, trying to gather all of the different papers that come across in the neural fields domain. Currently, I think we have actually over 400 papers in this collection. If you have a paper in neural fields, please send us fill a form, Google form, and we'll add it to this repository. I found this personally very useful when writing related work sections for some of my papers. So I found it quite useful. We also have a CVPR tutorial. You can watch the tutorial. Okay, so with that, I'd like to thank my students. They did most of the work that I talked about, and the funding agencies. And I'm happy to take any questions.
I have a question. For the articulation calculated like in the future world. I know that for the laptop, in fact, we observe that point count is a lot symmetry.
Yeah.
How
Yeah.
you distinguish between which part is the least and which part is the best?
Yeah, good question. I don't. So if I remember the results, this is still work in progress. But if I remember the most recent results that Rahul has been working on, I don't think we had as much difficulty differentiating between them across instances. So we were able to correctly identify the keyboard as the keyboard and so on. But we were not necessarily able to canonicalize them consistently in terms of the global orientation. So I think the difficulty there is disentangling global force versus articulation. I think that's the difficulty that we're currently being faced with.
I don't have a question about the projection of the tensor field.
I read the paper.
The spherical harmonic. I haven't. So that's my question. I mean, in the PCA,
Yeah.
you optimize like the variation in cross direction.
Right.
And the projection of the spherical harmonics to the PFN, what does it do?
So there is no optimization that we're doing there. So we
No, but basically,
Yeah.
should, but otherwise there's no definition of that.
right. So that happens. So let me try to go back to that slide here. It's a bit slow. But anyways, if we okay, so if we extract this equivariant features here, like we have something that is equivariant. As long as we choose one direction as canonical, we don't care about which direction we choose as canonical. Right? So we just have to choose one of those directions as canonical. And that happens already in this step over here for single instance. So just having this part gives us, or at least for a single instance, it gives us a rigid force that when you apply this rotation to the initial force, you get something that is canonical. So the second bit is only to make it consistent across different instances. Because if we just focus on this one instance, we get a different canonical force for each instance. So the second reconstruction bit is only to make sure that they're consistent across different instances.
So if you did a class measure, but where is the loss? The loss, you want to get
Right. So this is essentially think of this as a rotation matrix. We apply this to the input force, and we want to make sure that this looks similar to this reconstruction.
I can always apply another all of them.
Right. So what we notice is that a different random seed for the network results in a different canonical force. So if we start with a different random seed, we get a different canonical force. Uniform distribution. Yeah, we can discuss this. Yeah. Yeah.
Like I was realization. But sometimes you have this person that you want an orange here or
Yeah.
you have color, but it seems that the ShapeCrafter don't produce that.
Right now there is no texture; it's only geometry. That's actually fair criticism. So there are some texture properties that do get reflected in shape. For example, if you say something like a metal chair, metal is like a material property, but it still affects the way the geometry looks. It's like much smoother and so on. So you do see some of that happen with ShapeCrafter. But yeah, I think modeling appearance, I think, is something that we need to work on.
Have you think about like can the generate model to the arrangement, the layout,
Yeah.
the indoor layout?
Good question. So right now we are only looking at rearrangements, not arrangements. So you have a cluttered scene. You want to rearrange this into an organized scene. But this is not a generative model necessarily.
Add a sofa.
Right. I think that would be an interesting next step. Daniel Ritchie, also faculty member at Brown, he does a lot of work with that.
Can you talk more about the feature or the feature grid that you have in
Yeah. So in ShapeCrafter, if I understand correctly, we extract features from bird, and then we have linear layers. I believe it's 2 layers. No non-linearity, just the linear projection, right? And then we project it onto the grid. So the feature gets projected on each grid cell. It's just a simple projection, right? So the feature size might be 256 cube, for instance. Right? You just take the bird features, push it through an MLP, and you produce something that's 256 cube.
I see. What changes is actually the channel that so the channel there can have different number of words. So that's what the essentially the
Right. So it's kind of like a reshape operation, but through a linear projection.
So is that just that you have like a staple that that's like L-shaped, but did you see some L-shaped not?
Right. So I think a better example is this legs of a chair that look like armrests. So I mean, it's not perfect, but it looks like the legs are now flatter and wider. Right? It's kind of like an arm, what you would see in armrests. Right? Yeah. So this was definitely not seen during training. We had no examples where legs look like armrests. But I mean, there are limitations to the out of distribution capability. Right?
Yeah.
So it probably generalizes to some extent, but not too much.
Yeah, but I guess I was just confused. Never seen an L-shaped table.
I see. Right. I'm not 100% sure about the L-shaped table, but definitely the semicircular table and the legs that look like armrests did not exist.
Yeah.
So
No, it's
One question I had was like for the language processing part.
Yeah.
Have you thought about that propagating with respect to the first variable? So then you can like see. So maybe like I say with so like I give a prompt, then give me an image. That image is actually not what I want. But I also have the oracle image that I want. Then maybe I can back propagate with respect, like with using the oracle image, back propagate with respect to the prompt variable, and then see like maybe what the correct prompt would be to get that oracle image.
yeah, potentially. I think there's definitely variations of this that can improve. Right now, we just use, I believe it's fixed the rates. We don't do anything with God is fixed just because it's from. But yeah, I think there's definitely kind of try to optimize back prompts with that.
All right. Thank you very much.
Yeah, thank you all.
I have one more question.
Sure.
One question.
If we have time, yeah.
So they say together with the canonical, then they invariant.
Correct. Yes.
So if you output the invariant directly from the business side, but you can print out for all the
I see. Okay. So
because the event actually does something like
right. Yeah. We probably tried early versions of that. I don't remember exactly. And we went through like a lot of iterations of what worked and what didn't, essentially, right? And this insight that if you have 2 different things that produce equivariant features, you take the dot product of them, right? That gives you something invariant. That seemed to work the best in some of the experimental results that we did. So we probably tried like an early version of that. I don't remember exactly what was wrong with that, but I think the first thing that we tried was to just apply TF-trends on the point cloud, and that didn't seem to work as well.
So the canonicalization is just by contraction. And then now, because of the PCA,
Right. Yeah.
Here, that's the definition, but if I so you say what is canonical, how
So what is canonical in this case depends on how you start the network. So for every random seed, so if we train the same network twice on exactly the same data set, but with different random seeds, you get different canonical orders. So it's not fixed for the, so like PCA, there is no notion of a principal axis that it always finds. Right. So I mean, symmetry is an issue here. Right? So like we don't deal with symmetry. Yeah. Correct, yes. Yeah, PCA will always find the same thing, but that is not the case with ConDor. Every time we start with random seed, it gives us a different canonical orientation.
I'm only that by the question that now we something that is invariant. If there are other things that are invariant, for example, you have the same only for the same.
Yeah.
In your data, you will eventually have some feature that is invariant. But
Right.
how does this encode the same, the code, or can it contain other information there?
So if you just use this, it just has the post that there is no other information. Right? Like the extra information actually comes from the higher order spherical harmonics, right? Like things like the segmentation that we do. Right? All of that uses this invariant feature that we get here. So it does not just this part has no additional information.
For single object, they'll always find the written code, but the tricky thing is it's partial. Why is it partial?
Forget the question. How can we find a canonical? How can we find that? I understand that the product, that the non-product equivariant is equivariant. But you just read over many inputs, how you can give you a code. This is what I feel. The Sridhar harmonics is equivariant, and the tensor is equivariant, and we take the whole product and it is invariant.
Invariant.
Maybe for the reconstruction process happens.
So
So you see that in either somehow.
So in this case, I think that's what the random seed does. So we have this MLP here, which takes the features of the TFM. And I think the random seed that we specify essentially acts as a selection operation. So exactly like the min function on SO3 or something like that, right? So it selects like one orientation to be the canonical orientation for that particular instance. But this still does not work over multiple instances. So we'd have to have this other branch that makes sure that across multiple instances, we still have this this kind of a relationship between the reconstructed point cloud and the rotated point cloud over here.
And the in there
Is this one? It's a bit notation heavy. The paper has all the. I'm happy to talk about this, describing the notation.
The MLP has constraints of weight.
you are dismissed.
Sorry, say it again.
The MLP is also constrained to be
No, it's just an MLP. Yeah. Right. That's it.
IDI, that's one way.
So these features are equivariant, but there are no constraints on the MLP. This is not an equivariant. It's just an MLP, normal MLP. So depending on how you see this MLP, it essentially acts. It selects like one invariant. You say invariant rotation here, like it selects one rotation that is consistent. So it kind of acts like at least that's my interpretation is in spherical CNNs, you do like a max operation to identify one